Today we're going to talk about rocks and rockets. And let's start by talking about our Earth. And 4.5 billion years ago, something happened. There was an explosion, we believe, on the sun, and that is what has created our Earth. Let's have a look at the process. So here's our Earth now. That's not what it looked like 4.5 billion years ago.
Our solar system, 4.5 billion years ago. At its center, the young sun.
The theory that emerged was that the sun was surrounded by a cloud of dust and gas, and as that cloud cooled, little grains of minerals formed. So all these little grains of minerals floating in this gaseous cloud are moving around the sun, and they start to bump into each other.
But there was a problem with this theory. Nobody could explain how colliding microscopic mineral grains could ever create an object the size of a planet. Then, in 2003, an experiment on board the International Space Station accidentally provided extraordinary new evidence. Astronaut Don Pettit wanted to see what happened to different substances in the zero-gravity conditions of space. He did a simple experiment by pouring some salt into a plastic bag and shaking it. The results were astounding. The particles immediately began to stick to each other, forming little clumps, all held together by tiny static electric charges. Scientists realized that if grains of salt stuck together in space, then so could the mineral grains in the solar dust cloud. Here was real evidence for the fundamental mechanism that kick-started the formation of the Earth. As mineral grains in the solar dust cloud bumped into each other and stuck together, they grew into small pieces of rock orbiting the sun. Over the next few million years, some of them collided and grew bigger. Many of these rocks are still orbiting the sun today. They have drifted for the past 4.5 billion years, unchanged from when they first formed. Occasionally, they fall to Earth, and we call them meteorites. They provide scientists with an incredible window onto the past.
We brought what's called a stony type of meteorite. What the scientists do then is slice across it and look on the inside. And to a planetary mineralogist, you start seeing all kinds of wonderful things.
This meteorite contains minerals and metals from every part of the solar dust cloud.
So what we're looking at is the assemblage of all these little ancient materials that were floating around the sun in the nebula of dust and gas. And when they hit each other, they gradually aggregated into solid bodies, which got bigger and bigger.
Gradually, billions of these rocks grew as they orbited the sun. First to the size of boulders, then as big as houses. And they kept on growing. When an object reached about half a mile across, its own gravitational pull became strong enough to draw other objects towards it.
Some object in this huge number of objects going around the sun, one of them had to be the biggest. And as soon as it gets bigger than the others, it's sweeping up more objects, just like you're driving through a cloud of mosquitoes at night in your car and the front windshield's getting hit more often. So the bigger it is, the faster it grows. And the faster it grows, the more gravity it gets, and that pulls in more objects. So the biggest object starts to run away from the crowd. It starts to grow fastest.
And that biggest object was the fledgling Earth. Soon, the young planet had so much gravitational pull that it began to attract bigger and bigger objects. As they crashed onto its surface, Earth's size increased with every impact. The bombardment was so intense that it only took about 30 million years for the planet to grow to almost its present size. The young Earth was made of billions of pieces of rock randomly stuck together. But geologists know that the modern Earth is not like that. Below the surface, Earth is separated into distinct layers: a thin crust, then a massive dense layer of rock called the mantle, and at the center, an iron and nickel core. Some extraordinary event must have occurred to transform the interior of the young planet. Geologists now believe that soon after it formed, the Earth completely melted.
Originally, the Earth was probably just a big collection of rocks like this, but it heated up to the point where these rocks all melted. And when that happened, the denser elements sank down through to the very core of the Earth, and the lighter elements floated at the top.
The huge gravitational pull dragged the heavy iron and nickel down to form the core and separated the rest of the planet into layers. What caused such a huge mass of rock and metal to heat up in the freezing depths of space puzzled geologists for many years.
We think it's from the incorporation of very hot radioactive elements. They're out there floating in space. As the Earth accretes, it includes some of this ferociously hot material. As it gets inside there, it begins to heat up the rocks around it. And if you build the Earth fast enough and you incorporate enough of this really hot radioactive elements, it'll be enough to melt the Earth from the inside out.
Only 30 million years after it began to form, Earth had become a giant round ball of boiling liquid rock and metal orbiting the sun.
Imagine a totally molten world. I mean, it had molten magma oceans, no dry land anywhere, no water, just flowing lava everywhere.
The temperature of the molten Earth was now a staggering 2,000 degrees. But at the edge of the planet, the vacuum of space is a constant minus 450 degrees, almost 2,500 degrees colder. The surface rock could not stay molten for long.
It's cooling from the outside in. So from the outside begins to crust over, and you get this little scab, like on a wound, of cooled rock, but still really hot, and then gradually begins to cool from the outside in.
In less than 1 million years, Earth's surface was covered in a thin crust. But volcanoes still spewed out lava and choking gases. Meteorites rained down in a constant bombardment. Earth had a long way to go before it could support continents, oceans, and life.
That's what the evolution of the Earth looked like 4.5 billion years ago. So if we take that 4.5 billion years and we turn that into 24 hours and we look at the evolution of Earth and life over a period of 24 hours, this is what it would look like.
Life. With an estimated 3.8 billion years of existence and evolution on Earth, it's an odd thing indeed. So how did we get here? And what would the Earth's 4.5 billion year timeline look like compressed into a normal day of 24 hours? The story begins early in the morning, around 4 a.m., with the rise of the first simple single-celled organisms. However, these organisms are destined to spend quite some time alone. At 1 p.m., a simple cell engulfs another, creating a symbiotic relationship and the first eukaryotic cells, or cells with internal organs. At 6:30 p.m., these cells begin to form colonies, and thus the first multicellular life develops. But it isn't until 8:30 p.m. that sea plants appear, and 20 minutes later we suddenly see animal life erupt in an explosion of inventiveness. Jellyfish, the first true vertebrates, trilobites. Incredible diversification begins to take place, and just before 10 p.m., plants begin to appear on land, followed by land mammals. By 1024, the Earth is covered in carboniferous forests, and the first winged insects appear. Many reptiles dominate the land with less than an hour left, but a mass extinction event allows dinosaurs to storm the scene and remain until 11:41 p.m. when they too suddenly vanish. And so begins the age of mammals. In the last few minutes, apes split from the old world monkeys, and with only 1 minute and 17 seconds left before midnight, humans emerge. All of the recorded human history fits within a few seconds, an individual life lasting barely an instant. All a culmination of 3.8 billion years of life.
So the evolution of the Earth and life, we can look at it as a representation of the length of an arm. So right where the elbow is, that could represent 4.5 billion years ago when the Earth was formed, and this would be part of the Precambrian. So if we move down the arm towards the thumb just a little bit onto the forearm, that would represent 3.8 billion years ago, and that really was the beginnings of life in the Precambrian. These were single cell organisms. Not much happened in terms of evolution of life from 3.8 billion years down to 540 million years. And that can be represented by the middle of the palm of the hand. So at 540 million years ago, we call that the Cambrian. And during that time, there was an explosion of life. Let's have a look and see what that's about.
If we could go back in time, before fish, before complex animals roamed the seas, and before the Cambrian explosion, we would find only simple creatures. The course of life was relatively slow. Sponges, flower-like organisms, and flatworm-like animals dominated the ocean realm. Then, evolution took an abrupt turn. Suddenly, wondrous new life forms filled the watery world. A marine worm called Achaea was remarkably complex and mobile. Survival depended on competition for food, and the ocean became a realm of hunter and hunted. The Cambrian was a time full of sudden danger. Even in such a savage world, Anomalocaris stood out. Nothing matched it for its sheer size and killing efficiency. Snaring its prey with its two powerful front claws, it was a swift and deadly hunter. Only slightly lower on the food chain, another fearsome predator prowled the oceans. Opabinia had 5 eyes at the top of its head, and its own grasping claws to snare the weak and unsuspecting. To counter such ferocious predators, animals adapted new defenses. Canadia, a worm-like creature, sported protective bristles along the length of its body. essential armor for a slow-moving beast. Wiwaxia also glided on the ocean floor, depending on their elongated spikes for protection. What caused this phenomenal eruption of life, and what impact did these fantastic creatures have on Earth?
Some of these are magnified times 12, like the Swaptia.
Well, that's fantastic. Look at the translucence of it and all the detail of its appendages. This is the biggest Pikaia I've ever seen.
Well, it's enlarged 12 times. That's 12 times bigger than the life-size one actually would be.
I guess that's right. The life-size ones would have been about 2 inches long, like this.
Yeah, not very big.
Evolutionary biologist Rudy Raff is obsessed with just these questions. As a leading authority on the Cambrian explosion, he consults with those who seem to make extinct animals come back to life.
It would seem likely that there's not a single cause for a unique event like that, but we don't know. It was a unique event in Earth history. And there have been a number of hypotheses that have been put forward, and the hypotheses are good ones, and they include a real diversity of ideas. For example, that there was a genetic revolution that took place.
The genetic revolution of the Cambrian period could never have occurred without Earth's first primitive animals, the sponges. They had existed for millions of years, establishing the way cells interact to build an animal. Building on the cellular framework established by sponges, flower-like cnidarians were the first animals to develop the revolutionary ability to move. Finally, life began to evolve in dramatic new ways with the appearance of flatworm-like animals. This was the first creature to embody the genetic blueprint of a hunter, complete with a head and a primitive brain set near sensory organs. But reaching a critical threshold of genetic complexity was only part of what triggered the Cambrian explosion.
Another idea was that animals were evolving, they were small, but something changed ecologically. Perhaps the oxygen levels arose. And the result of that was that animals could become larger. A third possibility for why the Cambrian explosion happened is that it was an arms race, that some animals learned to become predators. They began to eat other animals. And as soon as that happened, of course, now the arms race begins, because there's an advantage to avoid being eaten, and there's an advantage to eating. So an arms race begins, an arms race that hasn't ended yet in the animal kingdom. This is still driving evolution even now. And I think it's likely, in fact, that all of these explanations probably reflect some part of that truth of what happened to make the Cambrian explosion.
So 540 million years ago is a very significant time in the evolution of life, really the true beginnings of the flourishing of life. Now, if we continue using the hand as an example of the evolution of life, and we continue from the center of the palm down towards the middle of the fingers, that would represent 200 million years ago, which is known as the Jurassic, and there was the beginnings of creatures like dinosaurs, and then that evolution continued with the beginnings of birds and insects. And then if we look at the very end of the finger, in fact the end of the fingernail, that represents 6,000 years ago and the beginning of man. So the creation of man from its beginnings as an ape all the way through to who we are today. So it's interesting to consider time from the beginning of the creation of Earth 4.5 billion years ago to what it looks like today with oceans and continents. Let's have a look at that evolution. So as the Earth evolved from what it was in the beginning, which was a single landmass, it continued to evolve into separate land masses that we refer to as continents. So single landmass, which we call Pangea, to our continents as we know them today. Let's look at how that...
The idea that our planet's continents drift around the globe, periodically glomming together and breaking apart, is at least 200 years old. But most geologists didn't believe it until the 1960s, when mounting evidence made it clear that the Earth's crust is broken up into fragments, and that those fragments, called tectonic plates, are moving. And these days we directly track that motion, with millimeter precision, from space. The common simplified explanation for why tectonic plates are moving is that they're carried along on currents in the upper mantle, the slowly flowing layer of rock just below Earth's crust. Converging currents drive plates into each other, diverging currents pull them apart. This is mostly true. Hot mantle rock rises from the core and moves along under the crust until it grows cool and heavy and sinks back down again. But the plates aren't just passively riding these currents around like a bunch of suitcases at the baggage claim. They can't be, because some of the plates are moving faster than the currents underneath them. For example, the Nazca Plate, a chunk of ocean crust off the west coast of South America, is cruising eastward at about 10 centimeters per year, while the mantle underneath it oozes along at just 5. Neither tectonic plates nor luggage can move faster than the belts they're riding on unless something else is helping to push or pull them along. And some of Earth's plates, it turns out, are pulling themselves. When an ocean plate collides with another ocean plate, or a plate bearing the thick crust of continental land masses, the thinner of the two plates bends and slides under the other. As the edge of the sea floor sinks into the mantle, it pulls on the plate behind it, the same way a chain dangling further and further off a table will eventually start to slide. The bigger the sunken portion of the plate becomes, the harder it pulls and the faster the remaining plate behind it moves. You can find where this is happening just by looking at Google Earth. The incredibly deep, narrow ocean trenches visible off the coasts of some continents and island chains mark the creases formed as ocean crust plunges downward, bending the edge of its neighbor in the process. What's more, these chunks of seafloor are actually helping to drive convection in the mantle beneath them. Sunken slabs of ocean crust block flowing rock from moving further sideways, forcing it to turn downwards and sink. And eventually those slabs get too heavy and break off, plunging slowly toward the core and creating a suction force that pulls mantle material along behind them. So in some ways, seafloor crust is really more like part of the conveyor belt than something riding on top of it. The continents, on the other hand, are baggage.
So this process of continents moving is known as continental drift or plate tectonics. And we see evidence of that around the world. We see places such as India where plates are moving together. So India is moving towards the continent of Asia and creating mountains. So as the plates converge, as India gets closer, it's creating mountains, including the Himalayas, and that would include Mount Everest. So that's where plates are coming together and pushing one continent up against the other. Now there are other places in the world, such as Iceland, where the plates are pulling apart. So in the case of Iceland, the North American plate is moving to the west and the Eurasian plate is moving to the east, so it's separating. And I've had the opportunity to walk along the pathway representing the separation of the North American plate on the left and Eurasia plate on the right. So our Earth is made up of 2/3 water and 1/3 rocks, and that's what we want to focus on today, are the rocks. So there are 3 types of rocks. The first type of rock we're going to talk about either looks like it has particles in it or it's layered, and we know this rock type as sedimentary. And this is what it looks like in the field. You can see the prominent layering of the rocks, so sedimentary. There's another type of rock that is either speckled, as you can see the one on the left hand side, or one that is very fine grained and often has holes in it. So the one on the left we refer to as igneous. The one on the right we refer to as an extrusive rock. And when we look at the difference between the two and how they're formed, intrusive rocks form deep in the earth as molten material that slowly rises towards the surface, doesn't get to the surface, and cools and crystallizes to form intrusive rocks. Extrusive rocks, the ones with the holes in them, is the molten material that gets to the surface and forms lava. We've seen examples of this in Hawaii, for example. So it's the combination of either extrusive or intrusive that makes up a rock type called igneous. The third rock type is a rock type that looks a lot like a sedimentary rock in that it's layered, but it turns out that these types of rocks are metamorphic rocks. And metamorphic rocks are formed deep in the earth as a result of pressure and heat. They form sort of squiggly layers. So the three rock types, igneous, sedimentary, and metamorphic, are part of a rock cycle. So igneous rocks can become sedimentary rocks can become igneous rocks, sedimentary rocks can become metamorphic rocks can become sedimentary rocks, and metamorphic rocks can become igneous rocks, and igneous rocks can become metamorphic rocks. So let's have a look at what this rock cycle is all about.
Rocks are everywhere. They are large and small, heavy or light, porous or dense. But rocks in some shape or form can be found all over the planet. Different types of rocks are formed in different ways. There are three main types of rock: igneous, sedimentary, and metamorphic. Igneous is a word that means fiery. Igneous rock is formed when magma or lava cools. Sometimes magma cools slowly underneath the Earth's surface. This forms intrusive igneous rock, like granite. Other times, lava cools when it comes to the surface in a volcanic eruption. This forms extrusive igneous rock. Some examples of extrusive igneous rock are tuff, obsidian, and pumice. Igneous rocks make up about 95% of the Earth's crust. The next type of rock is sedimentary rock. Sediment is small particles of sand, mud, and organic material that settle to the bottom of water or land areas, often lakes or oceans. Sedimentary rocks are formed when sediment accumulates over time in deposits that form layers. These layers become squeezed and compressed over time until they consolidate into a rock. Sedimentary rocks are the types of rocks in which fossils may be found, since the process of forming sedimentary rocks can preserve plant and animal remains that are deposited into the sediment layers. Some examples of sedimentary rock are limestone, shale, and sandstone. The third type of rock is metamorphic rock. The word metamorph means to change form, and metamorphic rock is rock that has been changed by extreme heat and pressure. Sedimentary rock, igneous rock, or even other metamorphic rocks can be changed by heat and pressure into new kinds of rock. Metamorphic rocks can be formed by being deep under the earth where pressure and temperatures are high, or when rock near the surface is heated up by the movement of tectonic plates or magma. Different types of rocks become different types of metamorphic rock when exposed to heat and pressure. For example, shale becomes slate. Sandstone becomes quartzite. And limestone becomes marble. Rocks are slowly but constantly changing in something known as the rock cycle. The rock cycle begins with magma, or hot melted rock, deep beneath the Earth's surface. This magma becomes crystallized, becoming igneous rock. These rocks begin to erode or break down into small pieces because of wind, water, or other forces. The small fragments of rock are carried away as sediment when water passes over them, and are deposited in layers, which eventually become sedimentary rocks. Then, some sedimentary rocks are pushed below the surface due to tectonic activity, where they are exposed to heat and pressure, transforming them into metamorphic rocks. If the rocks are buried even deeper, they may melt and form magma, starting the cycle all over again. Of course, sedimentary and metamorphic rocks can be eroded into sediment, and igneous rock can become metamorphic rock or lava. But one way or another, rocks all over the world keep changing from one form to the next.
So 1/3 of our Earth is made up of rocks. So what are rocks made up of? So let's look at a chocolate chip cookie. It has ingredients: sugar, flour, oats, chocolate chips, raisins, so on and so forth. So those are the ingredients of the cookie. That's what makes the cookie up. If we look at a rock, it's made up of ingredients as well, and we call those minerals. So this is an intrusive rock that's made up of minerals such as quartz, feldspar, biotite, amphibole, muscovite, and magnetite. So there are a lot of minerals that make up rocks. So in this case, we looked at quartz, feldspar, biotite, muscovite, amphibole, and magnetite. So when we look at minerals that make up rocks, what are minerals made up of? Minerals are made up of elements. So there's many elements that make up minerals. So there's many minerals. There's thousands of minerals that make up rocks. There's 118 elements that make up minerals. And those elements, we can see them on the periodic table. So just to test your listening skills, we're going to look at the uses of various elements, all 118 elements. Here we go.
And now, ASAP Science presents the elements of the periodic table.
There's hydrogen and helium, then lithium, beryllium, boron, carbon everywhere, nitrogen all through the air with oxygen so you can breathe, and fluorine for your pretty teeth, neon to light up the signs, sodium for salty times, magnesium, aluminium, silicon, phosphorus, then sulfur, chlorine, and argon, potassium, and calcium so you'll grow strong, scandium, titanium, vanadium, and chromium, and manganese. This is the periodic table, no gas is stable. Halogens and alkali react aggressively. Each period will see new outer shells where electrons are added, moving to the right. Iron is the 26th, then cobalt, nickel coins you get. Copper, zinc, and gallium, germanium, and arsenic. Selenium and bromine film, while krypton helps light up your room. Rubidium and strontium, then yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silverware, then cadmium and indium, tin cans, antimony, then tellurium, and iodine, and xenon, and then cesium, and barium is 56, and this is where the table splits, where lanthanides have just begun. Lanthanum, cerium, and praseodymium. Neodymium's next to promethium, then 62. Samarium, europium, gadolinium, and terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Hafnium, tantalum, tungsten, then we're on to rhenium, osmium, and iridium, platinum, gold to make you rich till you grow old, mercury to tell you when it's really cold, thallium, and lead, the bismuth for your tummy, polonium, astatine would not be yummy, radon, francium will last a little time, radium, then actinides at 89. This is the period periodic table, noble gases stable, halogens and alkali react aggressively. Each period will see new outer shells will electrons are to the right. Actinium, thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, isonium, fermium, nobelium, nobelium, lawrencium, rutherfordium, wm, sprigium, boreum, hesium, meitnerium, nepsidium, rucanium, copernicium, natrium, flerovium, pentium, livermorium, septium, noctium, and then we're done.
So the combination of minerals makes rocks. The combination of elements make minerals. Certain elements, when combined, make minerals, such as the combination of sodium and sulfur would be one combination that makes a mineral. The combination of sodium and chlorine makes salt. That's another mineral. And so it's these combinations of elements that make minerals that ultimately become the products that we use every day. Television sets, cars, cell phones, bikes, tires, all kinds of different things that we use on a daily basis. Really, all of these products originally came from rocks, from minerals, from elements in the earth. So, for example, a combination of these elements here creates cell phones. In fact, a cell phone is made up of about 72 elements. So we have a rock, and within the rock there are certain elements, and in this case, copper. So what we do is we extract the copper to make products like cell phones. So how do we do that? We do that through a process called mining. So going from a rock to a cell phone, we begin that process with geologists searching the world for deposits of copper. Once they're discovered and the deposit is worthwhile extracting, then we bring in big equipment to extract the copper from the earth. We process it to remove the copper from the rock. We concentrate it. We take that concentrate that contains copper and we put it on a ship and ship it to a refinery. And that refinery refines the copper and turns it into products that we can use. So in this case, copper wire. And then when we're all done the mining operation and the extraction, then it is the requirement of the mining company to restore the earth as best as possible. So in terms of restoring, here's a picture of a former mining operation on Vancouver Island. And you can see the trucks, and this is an open pit mine. So once the mining was completed, a lake was created, and the lake was stocked with fish, and there was trails for hiking around the lake. So this is one example of restoring a mining operation to, as best we can, the original environment. So here's a tailings impoundment that was used in a mining operation. Once the mining operation was completed, the tailings impoundment was planted and new trees were created. So you can see the beginnings of restoring the environment to its original state. Here's an example of an open pit quarry gravel operation on Vancouver Island that was done in the 40s and 50s. And this is what it looks like today, Bouchard Gardens. So British Columbia is well endowed with minerals, and we have several mining operations, including copper and gold, molybdenum, lead, zinc, coal, barite, all kinds of different deposits that are currently being mined, and those products are shipped around the world to be refined. So here we are. So the big percentage of our natural resources in British Columbia are metallurgical coal, which is used in the production of steel. And you can see copper is a big component of our natural resource, and it's 23%. And we also have zinc, molybdenum, silver, gold, lead, and various other resources such as gypsum. So we've been talking about our Earth and the creation of our Earth, the evolution, and what our Earth is made up of, which is essentially 3 rock types. We have the sedimentary rocks, the igneous rocks that are broken into intrusive and extrusive rocks, and metamorphic rocks. And we know that because of the rock cycle, one of these rocks can become another one of these rocks. So intrusive rocks can become sedimentary rocks can become metamorphic rocks, and so the cycle goes. And we also know that rocks are made up of minerals, and there's over 3,000 minerals that make up rocks. And we also know now that minerals are made up of elements, and there's 118 elements in the periodic table, and we saw the uses of those products. And then we know that there are certain elements that are used to make things that we use every day. And so in order to extract those elements from the earth, we need to have a mining operation, a refining operation to create products that we use every day, cell phones, cars. Everything that you use comes from the earth and mining operations. And we also know now that when a mining operation is completed, the mining company needs to do its best effort to restore the environment to how it was originally. So thank you very much for listening to this presentation of Rocks to Rockets. I hope you've learned something about the Earth and all of the products that are around us every day that we use. Thank you.